All right, welcome back to Physics 12. And this week we're going to be starting a new topic, which is induction. So it's kind of a subset of the idea of electromagnetism. And this is going to be our first week of it, and talking about something called Lenz's law. So just to set the stage for this idea, scientists have discovered already that an electric current can generate a magnetic field. So we saw that ourselves with our right-hand rule. If you have a current in the direction of your thumb, you produce a magnetic field in the direction of your fingers, or vice versa for a solenoid. So we know that if we have a current, that can produce a magnetic field. So then the corollary, or the kind of opposite question was asked, which is, if a current can generate a magnetic field, can a magnetic field generate an electric current? And there was two scientists, Michael Faraday and Joseph Henry, that both independently discovered that they could, in fact. And so this is the idea of electromagnetic induction. So induction has the same root word as induce, which means to kind of force something to comply, or force something to make a change in some way. And so electromagnetic induction is when we have the generation of a voltage or a current due to changing magnetic fields. And I underlined the changing part because that is really the key to this idea. So Michael Faraday, how he did this is he had an experiment that was a similar setup to this. So what he did is he produced a electromagnet by having a current that's producing this magnetic field. And so he put that next to another coil that had some sort of either a meter or maybe had a light bulb, to see if you could measure a current or to measure a voltage in here. But look, this has got a current, we've got a magnetic field, and it's sitting here next to this other coil, and yet there's no voltage being produced. But what he noticed sort of by accident is that when he quickly turned off the voltage or moved the magnet away, watch closely at the voltmeter and see what happens. You'll notice that you see a little jiggle there, but only when it's changing. So if you were to turn this battery off, you'll see a little bit of current produced up here. And this is what Michael Faraday noticed as well. What was interesting to note is that the change of scale, it's kind of I'll explain what that means in a second, but the change of scale doesn't really matter. So the change of scale didn't matter. And what I mean by that is that it didn't matter if we increase or decrease the current, it would still create a change, as we saw here. Whether I turn the battery off or on, increasing or decreasing the magnetic field, that wouldn't necessarily matter. It would still produce a magnetic field. What does matter is the direction. The direction of the change did matter. Direction does matter. Okay, and we're going to see more about what that means. And so magnetic fields in and of themselves, if you look at this, magnetic fields in and of themselves don't produce a current. You only get a current when you change the magnetic field. Okay, so generated by changes in the field. Okay, so we're going to show a quick video. It's about a minute and a half. So I'm going to show this quick video here, and that'll give us a bit of a better view of a practical I would have liked to do if you were in class. So here you go. So what he's got, what this scientist has here, you'll see the video in just a second. I'll start. This is a magnet that's in his hand up on the right-hand side. These are 3 coils of wire getting progressively more and more wraps. And this is called a galvanometer. It's basically a very sensitive ammeter. So an ammeter detects currents. This just detects very, very small currents. In fact, the maximum scale here is 2 milliamps, so 2 1,000ths of an amp. So it's very, very sensitive, and we'll just watch the video here and we'll explain a bit better.
So starting with the small one, if I move the magnet into the wire loop, you saw that as the magnet was moving into the wire loop, the needle bumped up positive. But now the needle isn't moving at all. And this is a very important bit of Faraday's law. There's only a current when there's a change in the magnetic flux. It doesn't care how much magnetic flux there is through the coil. Right now there's a lot. All that magnetic field is through the loop. What matters is when it's changing. So now I'm going to pull the magnet out of the coil. And what you see is that while the magnet was leaving the coil of wire, the current was negative. So we get an opposite effect. And we'll talk a lot more about that. The effect is proportional to the number of windings in the loop of wire. So we should see a bigger effect through this loop and finally for the third loop. So we definitely saw a bigger current, went all the way to the maximum and minimum, and then I think we actually pegged out here. It went beyond the maximum this galvanometer will measure.
Okay, so that is essentially what we're seeing here. So this is one application of it. Now what we're going to see in the next couple of weeks is about learning about generators. So generators are a bit more high-tech than this, but you can see that you can create electricity. So if you had some sort of system that pushed a magnet in and out of a coil, you could produce a current each time, a small amount of current for a small amount of time. So this is a solenoid here, just a wrapping of wire. And when it's moved in one way, so when it goes in, you produce a current going in this direction here. And when it's moved out, you push a current going in the opposite direction here. And to predict that, to predict the direction, we have a law. It's not really a law per se, that's what it's called. It's called Lenz's law. And essentially, this is what it says. The induced magnetic field will work to oppose there's two ways of putting this. I like this way here. So it's going to work to oppose the change in magnetic field. Or you can say it'll work to oppose the motion. So let's look at what this is saying one way or the other. So in this case here, we pushed the coil, we pushed the magnet to the right. And so the magnetic field being produced here is going to be in the opposite direction. So this essentially, when the magnet is going into the right, this makes the solenoid a magnet where this is the north pole of the solenoid and this is the south pole. So it's pushing against the motion. So some sort of current is induced in this that makes this the north end of the solenoid and this is the south end of the solenoid. So it's pushing against the motion. Another way of looking at that is that as this magnet goes in here, there's more magnetic flux going in this direction here. And so to oppose that, this coil is going to produce a current that produces a magnetic field going in the direction here. So there's more flux, what's called magnetic flux. It's this idea of field lines. We're going to talk about them in a second. There's more flux going into the right. And so this is going to produce a current which produces flux going to the left. So some of my students in the past have liked to refer to this as the get the flux out of here law, because when you have flux going in, you want to get the flux out to oppose that. So yeah, there you go. Okay, so this, like I said before, it's not really a law in and of itself. This is just an application of conservation. So it's sort of an inevitable consequence of the fact that energy is conserved. So energy conservation is a law, and this is just a consequence of that law. So conservation of energy is the law. Lenz's law is just a consequence of that. So if you think about what this is meaning, what this means is, if we push this magnet into the right, there's going to be a current. Now that current has to get its energy from somewhere, right? Energy can't just come out of nowhere. And in fact, it's because I have applied force. So I've done work. I've applied a force to the magnet. So I'm pushing the magnet, applying a force. I'm moving the magnet over a certain distance. So I am adding energy to the system, and the energy comes out in the current in this coil. And so it's always going to be in a way that you don't get free energy, basically. I'm not going to go into too much detail, but this is essentially an application of conservation of energy. And just a reminder, this is from previous weeks, but when we're talking about if we want to figure out what direction a magnetic field is going to be, if we want to figure out that the field is in this direction here, for example, we use this other right-hand rule, like we've got over here, the right-hand curl rule. So my fingers here represent the current. This is for a coil of wire or for a solenoid. The fingers represent the current, and the thumb represents north pole of magnet, or the magnetic field direction. So in this case here, if we're saying that the magnetic field is to the left, if we use our right-hand rule, it's going to look something like this. So in order to produce a magnetic field to the left, if I use this hand here, the current is going to have to go this direction here. I'm going to draw this here. So the magnetic field is the direction of my thumb. In this case, it's pointing to the left. That means the current is going up and over. This would be the direction of my finger. So up and over, going from the bottom on the front to the top. So just like this picture that I've got highlighted right here. And same thing for here. If I want to produce a magnetic field going to the left, I have to use my hand like this. So the magnetic field or my thumb is pointing to the right, which means that the current is coming over the top and down this way here in all these loops of wire. Okay. So as we said, the electric current is generated by a changing magnetic field. I'm just writing B field for short. And so in order to really discuss EMF, or the voltage or potential difference that's created in this wire, we need to understand the idea of magnetic flux. So just a quick point, this B in our formula, this is called our flux density. So we often refer to it as magnetic field strength, but really the correct term should be flux density. And so if we think about a magnet, the magnetic field looks something like this, where all these field lines are going outwards like this and wrapping around to come back here again. The closeness, how close these lines are, this is what we're measuring for B. So this is our density of lines. So obviously when the lines are closer together, the density is greater, and we can also say the magnetic field strength is greater. So B itself is the flux density. Now flux is basically the overall total number of field. Okay, so flux density tells me how close they are together. The flux is going to be how many overall, you can think of it as how many field lines overall are going to be going through an area. So the total number of field lines through an area. Now for a loop of wire in a magnetic field, so let's say here's my magnetic field here, going this way around here, and I'm trying to figure out the flux density. So I attach a loop, I draw a loop right here. So you could pause the video if you want, or have a quick think. What is going to affect the total number of field lines that go through this loop? So there's three things. Two of them are more obvious. One of them is a little bit less obvious. But I've got my loop sitting right here. What can I do to change or increase or decrease the number of field lines that actually go through this loop right here? So if you've had a chance to think about it, or if you want to pause the video and you come back, this is essentially what I hope you come up with. So one of them would be the strength of the magnetic field, or strength of the magnet, strength of magnetic field. So if we have a stronger magnet, then there would just be more field lines being produced here for a stronger magnet. The second one is going to be the area of the loop. So if I were to make this loop bigger, you can see that more lines will be able to fit through that loop. And the third one is the orientation of the. So what I mean by that is if I were to take this loop, which I've kind of drawn, I've tried to draw in 3D, but essentially this is the front side of it and this is the back side of it. So it's kind of standing on edge on the paper here. So if I were to rotate this so it was lying flat, so that means that it would be parallel to the magnetic field, well then you can see that no field lines are going to go through this. If I rotate it so it's kind of on its side, then we can see lots of field lines will go through it. But if it was lying flat on a piece of paper, so you can imagine if I've got a ring lying on a piece of paper, and then also parallel to the piece of paper or on the piece of paper are field lines, none of them are going to go in the front and out the back in essence. So you're not going to see any field lines that actually go through the loop. They're all going to go parallel to the loop. And so hopefully that makes sense that if we look at this, the maximum flux is going to be when the loop is perpendicular. It's going to be perpendicular to the field. And it's going to be a minimum when the loop is parallel to the field. So in other words, let's say this is my ring. So I take off my wedding ring, I lie it flat on the paper here. So I've got a ring sitting this way. If the magnetic field is going this way, we can see that all of the field lines are going to go through the ones that are in this area are all going to go through the ring. Whereas if the field lines were going this way, none of them would go through the ring. So when they're parallel, none of them go through. When they're perpendicular, if they're either going into or out of the page, then we're going to have the maximum amount of flux or maximum number of field lines. So the idea of Lenz's law, I want to give us a chance to have these practice questions here. So Lenz's law tells us that the change in the induced magnetic field is going to be in such a way to counteract the change in the magnetic flux. So let's take a look at one. I'll do a couple of questions on our own, and then we'll give you a chance to pause the video and try to do the rest of them on your own. If we look at this one here, so in this first case here, so these are all start on the left-hand side and finish on the right-hand side. We're trying to figure out what direction the current is going to be in this loop, i.e. is it going to be clockwise or counterclockwise. So in this case here, take out your right hand, and again, I've drawn dots meaning that field is coming out of the page, and crosses or X's meaning they're going into the page. So in this first case here, we have flux that's coming up out of the loop. In the second case here, we don't have flux coming out of the loop. So just like I said before, like I said, my students sometimes like to say, you need to get the flux out of here. It's essentially being disagreeable. So if there's more flux coming in, you want to get the flux out of there. And so you want to do something to counteract that. If there is less flux, so if the flux is leaving, then it's get the flux back in here. So in this case here, we've got flux that was coming through the loop out of the page, and now that flux is left. So we need to get the flux back in here. And so to do that, we're going to try and make a current that produces this magnetic field. We get a magnetic field back to the way it was before, where it's coming out of the page. Now, if we use our right-hand rule, what direction would I have to put a current in this loop here in order to produce a magnetic field that's pointing upwards? So remember, in this case here, for a loop or for a solenoid, your fingers represent the direction of the current, and your thumb represents the direction of the magnetic field. So because we lost the flux, we need to get the flux back. So we need to produce a magnetic field that's pointing upwards. So our thumb needs to be pointing upwards, and we can see here that our fingers are going to curl in this direction here. So in this case here, if all of a sudden we were to remove, we had this initial starting condition here, and we remove the magnetic field, we're going to counteract that by producing our own magnetic field, which is going to, I don't know why it keeps doing that, it's going to produce a magnetic field to get back the one that we lost. Okay, now let's look at the second one here. In this case here, we had a little bit of flux coming up, and now we have lots of flux coming through here. So we can see there's a lot more dots, there's a lot more field lines that are coming through this loop. So because we're getting more and more flux, we need to get the flux out of there. And so in order to get that flux out of there, we need to produce a magnetic field that's going to try and counteract it. So if we want to go back to the way it was to start, where we only had a few field lines, we essentially need to think that we're trying to cancel this out. So we've got too many field lines now, so we need to try and cancel some of these out. We've got many of them. We don't want this many of them. So how can we go ahead and cancel these field lines? Well, we would need to produce a magnetic field that's going downwards in order to cancel out some of the extra flux that's coming up. If you want to produce flux going downwards, well, again, take your right-hand rule. If your thumb is pointing downwards, which is the direction you need to cancel out some of these new extra upward field lines, then what direction are your fingers going? Well, they are going to be going in a clockwise direction. So if my thumb is pointing downwards on my right hand, my fingers are pointing in a clockwise direction. So what I've done here is I had more upward flux. I want to cancel some of that. The only way I can cancel that is by producing some downward flux, which means I'll produce a current in this wire that's going to be pointing downwards. Okay, just like we saw in that first video. So there's 4 more examples here. What I would like you to try and do, so just to give you a recap, this is going from downwards to upwards. This is going from a little bit of downwards to a lot of downwards to a little bit of downwards. This is going from downwards to no downwards at all. And in this last case here, the size of the loop is what's changing. So I've shrunk this loop, but we can still see that there's going to be a change in flux in terms of the total number of field lines that are going through the loop now that the loop has changed size. So please pause the video here. Try these out. Just remember, if we're getting more flux in one direction, we need to get the flux out. And if we're getting less flux going in a certain direction, we need to get the flux back in. So try that out with your right-hand rule and come back after you've paused the video and found the answers for yourself. Okay, so hopefully you have paused the video and you've tried these here. Okay, so let's go through these one by one. In this case here, we had downward flux, and that changed to upward flux. So we want to go back to the way we were. So we need to produce some downward flux. So how do we produce downward flux to get us back to where we started from? Well, our thumb is going to be pointing downwards, and we can see our fingers will be pointing in a clockwise direction. Okay, in this case here, we had a lot of downward flux, and now we have lost some of it. So we need to get the flux back in here. So we need to point our thumb downwards to increase the amount of downward flux, which means we're going to have our fingers pointing in a clockwise direction again. Number 5, hopefully you're seeing a pattern here. Number 5 is going to be the same as number 4 as well. It's the exact same scenario. We had lots of flux, now we have less. Same thing here, we have lots of flux, now we have less. So to get more downward flux, we need to put our thumb downward, and our fingers are again going to be pointing clockwise. And last case here, if you were to somehow count the number of field lines, you can see that there's lots of field lines pointing upwards here, and now there's less field lines pointing up through the loop now. So we need to get more flux. So how do we get more flux going through here? We kind of need to add our own magnetic flux. So we need to produce our own magnetic flux to kind of keep the number constant. And to do that, we would need to have our thumb pointing upwards, which means our fingers are going to be going counterclockwise. Now, one quick thing to note, because it is going to tie into our idea of generators. Now, for number 6, I told you that we shrunk the size of the loop, but you could also think of this as, this is what it would look like from the top down if I were rotating the loop, kind of pulling one side out of the page and putting one side down from the page. If we look at a loop that's rotating, just like it was with our electric motors, if we rotate the loop, we're going to see less flux in there. And so when we learn about generators, we're going to see that it's essentially the opposite of a motor. So a motor takes that electrical energy and produces kinetic energy. But if we have a loop of wire in a magnetic field and we apply our own kinetic energy by rotating it, like a turbine or something, by producing our own kinetic energy on there, we can change the shape of the loop. And so we can change the amount of flux going through there, and so we can produce electrical energy. So a motor takes electrical to mechanical energy, and a generator takes mechanical to electrical energy, or kinetic energy to electrical energy. Okay, so we've had our fun. We've figured out the Lenz's law in terms of calculating or determining direction, but of course it's physics class, and what good is physics without formulas? So here is your formula. So for Lenz's law, that's just telling us the direction. This is our formula that we're going to use. So we're going to be talking about something called phi. So phi is the flux, or we just have magnetic flux, or just flux in general. So this is our phi symbol. B is flux density. And A is our area. So this is our area of our circle. This is our formula. B times A times cos theta. Okay, and then theta is to do with our orientation. So for now, we're going to ignore that. If we're talking about flux, the units that we use, because flux, this is measured here in Teslas. So this is going to be Tesla meters squared, because the area is squared, so Tesla meters squared, where 1 Tesla meter squared has another name which is called 1 Weber. 1 Weber is 1 Tesla meter squared. Or you could say that a Tesla is a Weber per meter squared. Remember, it's flux density, so it's how many Webers there are per meter squared. Okay. But typically Tesla is the standard unit for that, but you could call it a Weber per meter squared. So, as we said before, we can produce an EMF by changing the magnetic field, specifically by changing flux. In fact, we have another formula here, which is the EMF. So this is EMF, or electromotive force, or voltage, same idea. This is equal to negative N times delta phi over delta T. So N refers to number of loops, and the negative sign refers to Lenz's law. So it's just telling us it's going to be in the opposite direction. If there's more flux going up, then we'll produce more flux going down. So that's where that negative sign comes from. So another way of saying this is to kind of combine these two together. So you can say that EMF equals negative NBA cos theta divided by time. Because that's what the phi is. This phi, it's Greek letter phi. Phi is the change in flux, so N times BA, NBA. Okay, so let's try a few practice questions here. So we'll do this one together, then you can pause the video and try the next two examples after that. So in this first case here, we have a square loop of wire perpendicular to a 1.5 Tesla field. Now each of these sides is 2.1 centimeters. Well, I'm going to just skip ahead here. Oh, I'm just going to change this unit because we don't like to use centimeters. That's not our standard unit. So each side of this is going to be the same, and these are going to be 0.021 meters each. And our magnetic field, let's just call it into the page here. We just know it's perpendicular, but this is going to be sorry, I'm not sure what's going on with my pen, but this is going to be 1.50 Tesla. Okay, so what's the magnetic flux? Well, here's our formula. Flux equals VA times cos theta. Now, in this case here, theta is 90 degrees, and so these are perpendicular, and so cos of 90, hopefully you'll remember, is equal to 1, so this is just B times A times 1, or B times A. So this is going to be 1.50 times 0.021 squared. And this gives us a value, if you put in your calculator, this is 6.6 times 10 to the minus 4. And it's measured in Webers because we're talking about flux. Okay, so this one here, this example here, remember this is a diameter, so you have to think about what the radius is. So this should be 1.80 meters. I guess that's an important note there. So 1.80 meters, 50 turns of wire, that's our N, perpendicular to the 0.25 Tesla magnetic field. And all of a sudden, that magnetic field goes from 0.25 Teslas to 0 Teslas. And the time it takes that is 0.100 seconds. So what is going to be our average EMF? So try this question, and then try this question after you pause the video, and we'll, after you try them, then we'll go through the solutions. Okay, so in this case here, this is a circular coil, and it's 1.80 meters, which means the radius equals 0.90 meters. It's a big loop, maybe like a giant hula hoop. Okay, so we've got this, and there's 50 turns of wire, and the B field is 0.25 Tesla, and the time is this. So we know that EMF is equal to negative N times the change in phi divided by T, or divided by delta T. So we also know that our delta phi, negative N times, now phi equals B times A. Now in this case here, the A is not changing, it's just our B. I'm just going to change this to N times delta B times A divided by T. So this is the change in flux is based on the change in the flux density, or B, and we're going to multiply that by A and divide by T. So here we go. This is going to be negative 50 times, now it's going from, the final is 0, and the initial is 0.25. So this is going to be 0 minus 0.250 times the area, which is pi times 0.9 squared. And we're going to divide all that by 0.100 seconds. And the final answer you get for this one should be approximately 320 volts. That's the voltage we would get in this wire, or in this coil of wire. Okay. Lastly, we've got a circular loop of wire, radius 2.5 centimeters. So here is our radius. Now it starts out with a field of 0.02 Teslas, and then it ends up being 0.01 Tesla. So I'm going to draw this way. There's two loops. The loop size doesn't change. The radius is 0.02 centimeters. And in this case here, we start out with, it's going into the page. So we start out with a strong magnetic field, and we end up with a weaker magnetic field. By the way, when I draw these, don't necessarily get hung up on the number of X's that are going through the circle. We're just kind of looking at, in this general area here, you can see here on the left-hand side, obviously there's more going through here than on the right-hand side. It's just kind of an area, and the density here is representing the kind of overall density, but it doesn't necessarily mean each one line is anything specific in there. Okay, so it's reduced to 0.01 in the page, in the time of 0.10 seconds. So EM is going to be, I'm just going to do the shorthand, negative BA. Now the cos theta again is going to be, they're perpendicular in both cases. So the cos theta is going to be cos of 90, which is just going to be 1 to, or a value of 1. So this is going to be our formula here when they're perpendicular, negative MBA divided by T. So again, this is going to be, it's a single circular loop. So it's going to be negative 1 times the magnetic field. In this case here, final minus initial is 0.01 minus 0.02. I'm going to multiply that by the area, which is pi times 0.025 squared. And that is happening in a time of 0.10 seconds. So you put this in your calculator, this is going to end up being negative 0.01. So our two negatives will cancel out. We'll end up getting the value of 2 times 10 to the negative 4 volts. So this is going to be 2.0 times 10 to the negative 4. And it's an EMF, or potential difference. So that's going to be our final value there. What direction does the current flow? Well, hopefully you remember our rule. So we had lots of flux in, and then we lost some of it. So we need to get some of that flux back. And the only way to get more flux in the loop here is to induce an EMF, which means if our field that we're producing is downwards, our EMF has to be clockwise from our right-hand rule. Okay, so that is the notes for the week. Please try half the practice questions at least. And lastly, you do have the assignment on Google Classroom, the series of questions. So give those a shot, and if you have any other questions, I will either get an email from you or see you fit on Wednesday. Or maybe I'll see you in class next week. Who knows? Talk to you soon.